So the problem set two, right? You are given two stimulus-based question. I think you should have seen the abstract or inserts. Okay, so typically, we gave you all something that is a little bit more realistic to what you expect from Cambridge exams. You can see that the insert isn't very long. They were our past lecture tests. Okay, so let me just discuss the first insert, which was last year's lecture test. Okay, so if you want a little bit of background to this, it's quite interesting because what happened last year was that I was in Australia for 2 months, not 2 months, 2 weeks. I wish I was there for 2 months. 2 weeks. Okay, then I was teaching a course on photochemistry, so I need to set an exam paper for photochem. It's a course, yeah. And then I found some research papers, so I set a exam for them, for the year 3 students there. Then when I came back here, I need to set for our lecture test, right? So I just modify and make it a bit easier and then took out things that are not necessary. So yeah, so this is the molecular switch, which you get it from here. Of course, there's no photochemistry involved because I didn't want to bother the students with a lot of other details. Yeah, so if you're interested, you can ask me for the papers. Okay, it's actually pretty interesting. So if you look at the abstract, actually a lot of it, you don't really need to use them for the question. Okay, so they mentioned that there's this state-of-the-art multi-responsive enamine molecular switch controlled by intramolecular hydrogen bonding. Sorry, let me just remove. Sorry, I just controlled by intramolecular hydrogen bonding. Okay, then smart materials, etc., etc. Okay, what is most impressive about this thing is it can switch between E and Z transition. Okay, depending on what you add to the system. Okay, so importantly, of course, you need to look at figure 1.1 because they are just using a very simple acid. In this case, is methyl sulfonic acid (MSA). You don't need to know the full name; just call it MSA. It's what we call an organic acid. That is even more acidic than what you can imagine. So I think the pK is less than 0. Okay, then you realize that when I started with E, right, after this particular nitrogen gets protonated, then it switched to Z. Of course, this is the conjugate acid form. Okay, so right now there are several questions you might have, because you notice that I have a number of nitrogen, but there's only one nitrogen that gets protonated. So the first thing you might want to recognize is in this particular system, why is it that one particular nitrogen is being protonated? You realize that later the question is being asked. Okay, so there's some context given. Okay, then the NMR part I'm not going to discuss now. Okay, so if you look at the question, they actually ask you, they give you some procedure. So this is quite common for H3. They will test you on stoichio. Okay, so they give you a lot of data which can be a bit prohibitive because it's, under exam stress you have to read through all this data, but then just take note that this is H3. So sometimes we can ask you the simplest thing in the most inconvenient manner. But anyway, if you read through them, you realize it's not difficult. Okay, so they are asking you Sec 3, Sec 4 stuff, calculate percentage yield. Then, of course, we look at a sample we have here. So, if you get the correct answer, you should get 71.9%. I'm not going to go through everything because I don't think this is something that most of you have problem with. But you might want to take note that there is probably a need for you to showcase why is one of the reactants the limiting reagent before you jump into your conclusion. Okay, so that's crucial in answering this question. Okay, then if you look at the next part, this is the slightly more difficult part. I remember marking it last year and a lot of people didn't answer it well. So they said that the zinc chloride is added to activate the reaction by providing an alternative pathway with a lower activation energy. So this question already tell you that the purpose of adding zinc 2 is to provide an alternative pathway with a low activation energy. So when you answer this question, you cannot repeat that statement, because repeating that statement doesn't help. Yes, so you have to tell me a little bit more. Okay, so what is the little bit more that you feel that you should address that? Because when you add your zinc, right, actually what's the purpose of adding zinc? I mean, without going a lot into the mechanism now, you will actually see that, let me just highlight for, oops, wait, let me just highlight this portion for you. Can you see that this portion, right, is actually added in? Okay, then of course there are more to it than to meet the eyes lah, because if I highlight further, it's actually, it includes this part. Yeah. Okay, then the other two groups, so-called leaves. Okay, so-called leaves. I mean, somewhere. Okay, living group, etc. So then, okay, even if you are not able to see this whole thing, right? Even if you are not able to see this whole thing, the simplest idea is probably to realize that this particular zinc, right, being zinc 2 is what we call a Lewis acid. So a Lewis acid tends to allow a Lewis base to coordinate to it. And in the process, once it's coordinated, the zinc center will have a positive charge. I mean, zinc itself has +2. So once there's a coordination, then it creates a formal positive charge on the oxygen. Then in that case, it allows the neighboring carbon to be electrophilic. Yeah, so we need an idea like this, like to generate, let's say, I mean, it can be the simplest answer, like to generate electrophile, for example. I think that works. Yeah, so you have to be a little bit, okay, this question on hindsight, of course, it might be easier if we ask you to draw mechanism or maybe give you a partial mechanism. I don't know lah. But I would say for a 1 mark question, you don't have to say too much, but I think the main thing is about the provision of the electrophile, okay, upon coordination. Okay, so there are a lot, I mean, I received a lot of answers last year, so most of the answers will talk about something related to lowering activation energy, etc. But I think the main thing is not about it. It is about that. I told you already. But then, how do you do that? What do you generate? Okay, so that's important. Electron source and electron sink in A. Okay, you realize that molecule A is actually quite an interesting looking molecule. If I'm going to just zoom all the way in, right? Okay, now you realize that if I'm going to just draw this structure out as a triple bond, okay, as a triple bond, then you will notice that there are 2 electron withdrawing sites over here. Okay, this is a bit hidden, so most people can't tell. This is a bit hidden. Okay, yes. Then if you can see, then you will struggle a bit lah. You'll be thinking which one to go. Yeah, but actually it doesn't really. Okay, I have a preference, of course, or rather there's a reality. The reality is that it should push towards the CN. It should lah. I remember back then when the students pushed towards this, I think I accepted. I think, okay, I cannot tell you for sure because I can't remember. That's 1 year ago, and we have been through a very traumatic 1 year. So I think I did accept, okay, but the reason why it's not the reality is because that will disrupt the aromatic system of the pyridine. But then again, you can argue that how do we know? Oh, yeah, so we don't know, right? Then that's why I accepted the answer. Yeah. Yeah, but for your great grand senior, etc., they learn about 3D now system, then yeah, that's fine. Okay, so an acceptable answer here would be this is the electron source, and then this is the electron sink at the end here. So you push all the way. Okay, like this lah. Okay, so your friend here did that. I mean, perfect. No issue. Okay, if you push to the end in the predinal ring, just make a remark. Don't need to mark it wrong, as in don't need to be so harsh, okay, on yourself. Yeah. Okay. Any questions? I don't know whether I can take questions, but yeah. Okay, I just move on first, because I also need to take a break. Quite tired. Keep talking and talking. I haven't even drink my coffee. Yeah. Okay. What's the other part? Okay, use the resonance structure you drew in A3. Show how it reacted. Okay, how it reacts with RNH2 lah. So RNH2 obviously is the primary amine with the lone pairs of electrons as the electron-rich site. Yeah. So the reason why this is being asked of you is, of course, once you drew this little structure out, you can tell that the nucleophile can attack here. Okay, if I don't ask you to, okay, you try to be fair lah. Let's say I don't ask you to draw, you cannot draw the mechanism at all because you will anyhow whack and then in the end things all hell will break loose, right? So yeah, so there's a need to guide you along the way. So you need to draw this and then pushed. Subsequently, whether you choose to protonate your O first or you choose to kick this group out first, actually it doesn't really matter. I think Cambridge don't really care about that because unless you've done the studies, if not you can't tell. So I think here they are quite chill about it, or rather we are quite chill about like however you draw from there. Yeah, but you have to draw from this structure. Okay. If you ask me whether got ECF back then, I also cannot remember. Depends on what you drew. Okay, so I can't answer that at this stage unless you show me your sample later. Yeah. Okay. So that's about it for this. I think this is a reasonable mechanism to, I mean, it's not too tough, but it's guided somewhat. Okay, then come back to reality because we need to ask you about why the other two nitrogens are not being protonated, right? Okay, so I think I reminded you just now that there's something to look out for. Okay, so there are several things you might want to be aware of. Number one is if you simply check the structure, right, you will notice that this particular nitrogen, okay, if let's say the lone pair is at the p orbital, so it is likely to form a continuous overlap all the way. Okay, so that means that the lone pair is resonance stabilized. You will ask, it's the same kind of question being asked, like, how will we know? Okay, the truth is, of course, we don't know for sure because it will always have a choice. Okay, so the choice is if it prefer to be sp3 hybridized, the overlap will be at an angle. Do you agree? You can try to draw it on your own. I think this is H2 stuff, by the way. I mean, I explain this to my H2 students every year when I'm year 2. So the system has a choice. Okay, it's not like a living thing. Okay, it doesn't like decide one time, today I take sp2, tomorrow sp3. It depends on the neighboring partner. Okay, so if the neighboring partner is a pi system, then electronically it is more favorable for itself to have the lone pairs of electrons on the p orbital in order to form the continuous overlap so that delocalization or some form of delocalization can take place. Yeah, so because there are delocalization exists, right? I would not expect the lone pair to be readily available to coordinate to a proton. Yeah, I spoke a lot, but actually answer don't have to be very long lah. Just say that it's sp2 and then lone pair at the p orbital, and that's about it, can already. Okay? But because my main role is to explain the answer rather than to tell you the answer, okay? Then, what about the lone pairs of electrons on the cyano? This. Okay, so that particular lone pair, right? It's a bit interesting because it's in sp hybrid orbital. So because it's in sp hybrid orbital, the percentage of s character is likely to be greater than this. Okay, so in that case, when your percentage of s character is bigger, then on the average, the lone pairs of electrons will spend its time closer to the nucleus on the average. So therefore, it is not that as available as the sp2 one to coordinate to a proton. So make it a weaker base. So with this explanation in place, you can easily argue YA, is it labeled as A? Supposed to be A, is it? Okay, anyway, it's labeled as A here. The lone pair is available. Okay, can. Yeah, so we will go slow lah. Cannot finish, never mind. I mean, we can always, I can always record the remaining part for your subjected. I mean, it depends on when it can be released, okay? But we will go slow. We don't have to do it very fast. Okay, yeah. What is this? When purified compound was studied, it was observed that the compound displayed exclusive E. Okay. Then, when I added the methyl sulfonic acid, the Z configuration dominates. I explain the observation. Okay. So, you know that it has got to do with the intramolecular hydrogen bonding. So let me just flip over here. Okay. Now, if I'm going to erase this thing, right, you will notice that if I'm going to just open up the bond here, the lone pair is available to form intramolecular hydrogen bonds. Yeah, so that means that there is indeed a preference for intramolecular hydrogen bonds if the lone pairs of electrons or at the pyridinal nitrogen is available. Okay, but then upon protonation, right, it's not available anymore. So since it's not available, then it has to make a choice because you know molecules, they want to be as stable as possible, right? So what kind of choice will it make? So if you look at this whole portion versus this whole portion, right? Yeah, in terms of steric demand, it's a bit greater, okay, as compared, as in if let's say, okay, if let's say there's a, if let's say there's a protonation over here, let's say this is protonated, okay, then when I compare this versus this, the one with the R and H facing inwards will have a greater steric hindrance, okay, as compared to the Z isomer. Yeah, so therefore upon protonation, right, there is a real need for it to switch configuration. Okay, so that's really the reason why, I mean, you can give steric as a reason in this aspect why there's a switch in configuration. Okay, so I'm just going to erase this just to make sure that things are not confusing. Okay, so that's why I switch, okay, from E to Z. Okay, so what's the kind of ideas you can give? So basically, students need to recognize the formation of intramolecular hydrogen bonding and how the E isomer is being stabilized. If you mention that somehow, you will get the credit. And then when protonation takes place, this is not possible anymore. Okay, and then therefore the steric hindrance will cause repulsion. Okay, so you can mention that. Yeah. Okay, so that's pretty much what you expect for at least until part C. Okay. I love this paper very much when I was in Melbourne last year. The reason why I love it is because of the NMR. How come NMR is good? Because, oh, sorry. Why is NMR good? Because we always test the students' NMR, right? By looking at how to do elucidation and ask you to assign. Actually, this is quite narrow. I mean, it's not narrow in the sense of, but usually that's one purpose of NMR, but there are a lot of purposes. So one of the purpose is what we show you here. It's a beautiful study, but the problem is we're not able, or rather they didn't publish very nice spectrum. Okay, I mean the spectrum is nice enough, it's colored lah. But of course, when it's printed for you all, it's blank white. So my apologies, but love to give you color. But yeah, so we try to make the spectrum look nice by zooming in. Yeah, but we can't get very nice spectrum from the data given. That's the best we can get. Okay, so I'm not going to attempt to go into the nitty-gritties like why is this singlet, doublet, multiplet, etc. because it's not necessary at this stage. Yeah, so there's only one thing that we need to do over here. The thing that we need to do is I think the question asks you to label, okay, the identity. Yeah, so the initial question, right, what we did was we asked the students to identify everything. But the teachers discussed, we realized it's a bit difficult. So, and last year COVID, right? But don't everything COVID and make it easy. Yeah. So we say, okay. We understand the student, etc. So we make it easier. Then you realize it's a lot more accessible, right? Because once you make it easier, basically what do you need to look at? So we gave you all the difficult ones already. We gave you the broad singlet, which is HF, okay, which is the platonic hydrogen. We gave you B and E. So actually B and E are like the difficult one to identify if let's say we don't give you, to be honest with you lah. Yeah, especially for E. Okay, so in all honesty, I think we have to be fair to the students. Yeah, I mean I think in this case it's quite fair lah. Then after that, all you need to do is just to identify the rest, which based on what you learn shouldn't be too difficult, because I think number one is you realize that there is a very beautiful singlet here. Okay, because it's a methyl group. Yeah. So anyway, to identify, yeah, just dump it in, and then you might want to check your answer first. Maybe I pause for 30 seconds, then I can drink my coffee. Yeah, you check. Okay. Yes. Then I'll explain if there's a need to. Okay. Yeah. I'm going to come back to this. Yes, I think this is fine because it's the singlet. Okay. Then of course for Hg, being next to a carbonyl group and the N, okay, wouldn't be too difficult. And of course 2 protons. I think the integration ratio it helps also. Okay, and then of course for the rest, what you need to do is, of course, you look at 7.35 and 7.73. There's a doublet and singlet. Then because you already identified the rest, then of course you can easily incorporate HD here, and of course HC. Okay, because they are next to each other. So if one is a doublet, it must be caused by HC. Okay, so HC is a triplet, it must be caused by HD and HB. Then of course the one that is nearest to the electron withdrawing end must take on the highest chemical shift, or must be the most deshielded. Okay, so that will be HA. And of course you have 111 here, so I think it's quite easy to identify that they must be part of the aromatic protons. We are aware obviously that identifying the individual aromatic protons is really beyond what you need to know, but this is a contextual based kind of question. So we are not throwing you deep into the water and asking you to identify. We give you some numbers, so the rest you can do some prediction, make some prediction. Okay. And then this comes the most interesting question here, which is with reference to 1.2. How does the switching takes place, lah? So okay, you realize that number one, right? The broad singlet. Wait, let me see. This broad singlet is shifted, so it becomes shielded. Okay, it becomes shielded. Then after that, right, your H, E, and B, your H, B, and E. Okay, where are they now? They get shifted downfield. Okay, they get shifted to, I think, 8.3 and 7.45. Let me see, 8.3. 8.3, 7.45 is here. 7. No, sorry, the other one. Here. And 8.3 here. Okay, so you realize that actually the shape looks a bit weird, right? Yeah, it's because there is some merging of the different peaks. Yeah, but that's not so crucial. Okay, so the reason why they want to go from 1 to 2 to 3 equivalent is basically to tell you that how the thing goes along the way. Of course, in the middle, there's a bit of mixture of the two isomers. Okay, and you notice that in a lot of this kind of experiment, right, after the whole thing, right, they will just whack everything in 6 equivalents, and they will try to see if you can get back the original amount of, I mean, they will add the base again to see whether you can get back the original compound, so as to prove that it is merely acid-base reaction that's taking place. Yeah, actually it's quite ingenious. Okay, I think there's a question being asked later on that, but I thought I can just address this first, since we are on the graph. Yeah, the reason is, you can never say for, okay, without much, right, you can never say for sure that this reaction is indeed acid-base or is indeed reversible. So you have to prove it by actually adding the base in to see whether you can switch the thing around. Okay, so that's what happens. Okay, so what are the kind of answers that is needed? Yeah, so don't really need to interpret a lot, but just to tell us how it's being shifted. Yeah, so for example, an answer like this will take all the boxes. Like for example, both HB and HE shifted from blah blah to blah blah respectively. So that's fine. Okay, so I mean it's written well. I would like to encourage you all to use the word respectively, because sometimes when you write stuff, we don't really understand what you're trying to say. Okay, so if you can't write everything out nicely, you can just write in I mean, you can just write simple sentences. Okay, so please write simple sentences if, let's say, you have problems expressing yourself. Okay, anyway, I was talking about this. So basically, this question, if you read the question, they ask you to describe in detail how the thing shifted. Okay, so basically, you just need to say, oh, these 3 peaks, like HB shift to where, HE shift to where, HC directly. Describe. Haven't explained yet. No need to explain. Okay. Then part 3 is to explain. So don't mix your answers up. That's why it's 3 marks. So this, okay. So originally 2 and 3 are collapsed. So now we compartmentalize them. Describe, and then after that ask you to explain. I think it's easier for students to get the marks. But we cannot guarantee that Cambridge does that, as you have seen from your lecture test. Your lecture test, we have that explain the percentage for the A and B products in E1. Yeah. So sometimes they don't compartmentalize. So it's difficult for you to understand what exactly you need to write. Okay, but in most cases they do. Okay, half the time they do, I guess. Really depends on how long. Okay, then how do we answer that? Then of course, you can say that, oh, once protonation occurs, then your nitrogen. Okay, wait, where's the nitrogen? Okay. So once this is protonated, right, it actually becomes a stronger electron withdrawing group because once it's protonated, it gains a plus charge. Yeah. So that withdrawing effect will actually cause the neighboring electron density around the H to shift. Okay, accordingly. Okay. So which explain why, which easily explain why the other two, like these two, actually shifted from 7.07 to 7.45 and 7.27 to 8.30. Okay, then how come, the interesting thing is, how come my protonic hydrogen become more shielded? Well, I mean, it's no longer involved in the hydrogen bonding, right? Yeah, so that could form, or that should form part of your SA. Wait, let me see where. Yeah. So, okay. So the student said that, oh, it's further away, etc. Right? But I think the focus here might be on the absence of intramolecular hydrogen bonding, which will actually make the answer a little bit more convincing. Yeah. So once I do not need to form intramolecular hydrogen bonds, my electron density is no longer as disrupted as it should. So it becomes greater. So it's more shielded. As you know, it's related. Um, in in the revision towards your prelim exam, you might want to look through some bits of the theory of NMR again, because some of these things might be important and they could save you these few marks. Okay, so that's one point I thought I could make here. Okay, then I think for the other part, I have explained the rationale of adding this. So I think your classmate wrote perfectly. I mean, is to deprotonate, neutralize, so it can prove that the same, etc. The reason why I put a little caret here, again, if you heard me, if you heard my last part, if you heard the last bit of my explanation, right, I actually said that it is to showcase that this whole event is basically acid-based and it doesn't change the integrity of the structures substantially. Yeah, but whether to write so much for 1 mark, again, I don't know lah. As in, I mean, I just tell you what I think I will write, but whether it is sufficient, sometimes Cambridge also not consistent. Sometimes they demand a lot for 1 mark, sometimes they don't. So I think I'll just leave it. Okay, then what suggest why the authors term that as molecular switch. Basically, you can write anything you want. So the main thing is they are able to switch between different configuration when you add a chemical. But if you know from your GP, right, you cannot use the same word, right? Switch. Yeah. So chemistry, I don't know how the Cambridge examiner will look at it, but I would say you can just talk about things like, you can even say change or alternate or navigate between the two configurations. I think that's fine. Okay, can, right? I don't know whether you recognize this part to like that is a switch, right? If let's say, okay, I mean the other side, I mean I can show you, like if let's say it acts as a molecular wire, right? I can just put on a UV light, I mean fluorescence or some lights, right? Or some chemicals for it to switch, and then it will break the flow of the current. Yeah, so it's quite an amazing discovery. Yeah, so I was quite fascinated with the paper. That's why but the paper itself, the bulk of the story is not about the switch. It's about something else, by the way. Yeah. Okay. Actually, this part is anything goes lah. You write anything, we give you the marks as long as you write something lah. Yeah. So please write something. So okay, my suggestion is in exam you probably will not be able to think of so much things to write. Yeah? So please control what you can write because you need to finish your whole paper. So I would think that one of the most amazing thing about this is probably the fluorescent part. But actually you can Google molecular switch, you come out a lot of stuff. Okay? So yeah, that's something you can mention. And I think that's the end of question 1. Okay, this question is a different flavor because you get a different kind of storyline. So the main thing about this question is that they highlights this particular dynamic covalent chemistry. Actually, whenever you read these kind of weird terms, you don't really need to care too much about it. Like, I mean, if you don't understand it, you just read through. But you sure see some stuff that you know. Like, for example, thermodynamic control. That's about it. And then after that, there's an interesting mechanism here known as nucleophilic aromatic substitution. And then they give you a lot of description here, blah blah blah. And then and also very very heavy stuff like 3, 4 point junctions, etc. Okay. And then some BET surface area, which might not be interesting. Then kinetic control. Okay, yeah. So these are some of the things. Then after that, there's a description on what is nucleophilic aromatic substitution. They tell you that it's important in the synthesis, and then abundant opportunity to do this and do that. Okay, so if you don't feel like reading a lot, just look at the diagram because it's more interesting. They mentioned that, okay, if I subject this interesting compound to 4, I will get this. So, which means 2 of the fluoro group, or rather, all the 4 fluoro group will be substituted. 1 equivalent, I get something interesting like this, observed. And then after that, I add in another equivalent, and then I'm getting 5 again. Okay, so they use potassium carbonate solutions. Potassium carbonate is very commonly used. So you might want to know that its most important role is deprotonation. Yeah. Why is potassium carbonate good? Because number 1, it's not a very strong base. So it doesn't hurt a lot of things. It cannot hydrolyze a lot of stuff, right? Yeah. So you notice that in research, they often use something that's very mild, okay, which is highly, desirable because I don't want the structure which I make to hydrolyze. Actually, on hindsight, we can easily ask you another question. Why can't I use sodium hydroxide? Then you might notice that the cyano group can be hydrolyzed. But we didn't ask that. Yeah. Okay. So it could be asked as well. So there's a lot of flexibility in asking questions. It's just how much we want to ask. Okay, part A is interesting because they ask you what is the essence of dynamic self-correcting. Then when you read through this, what can you tell? Yeah, so this part is also a bit difficult to mark because a lot of times we get a lot of answers, then we also don't know where to draw the line. Anyway, this was lecture test 2019, so your 19 batch. Is it 19 batch? 18 batch. Okay, I forgot which batch, but 2019, we gave this in 2019. Okay, yes, so okay, so we have okay, it's difficult to give an answer to this to be honest. So this is what was written by your classmate. When 1 equivalent of this is added, this takes place at 3 and 4. Okay, then T considered to be the wrong position. Okay, then 1 nucleophile attack. So it's a description while the other attack. However, when 1 more equivalent is added, right, then the same product, then the sulfur bridge are corrected. Yeah, so we can, no problem no problem. Yeah, but the dynamic part is not addressed Of course, you can argue that the answer give an indication that it's reversible. So can also I mean, if let's say there's a marker B, and maybe Mr. Lim or Mr. Lee say, hey, but this means reversible. Also can, so we'll give you the mark. No, really. I mean that's the kind of conversation we often have. Okay, so let's look at your grand senior or senior last year. This student anyway, okay, I want interesting student. Okay, so it is self-correcting because when compound 9 is formed, the reaction corrects itself, okay, by undergoing another reaction which produces 5 from 9. So only compound this is obtained at the end of the day. Okay, got a bit of extent, but never talk about the reversible also lah. So I put here can be refined further, but the idea is there, got a bit of idea. So yeah, so you can have hundreds of combination, okay, in your answers. But the most important thing is the absence of self-correcting and dynamic must be there lah. Okay, yeah. I have answered part B, so it's a base. Okay. But please, I want to use the word please. Be very careful. State the role and suggest what is needed. A base alone is not enough. You have to say that it's a very H2-ish kind of answer. It's to generate a stronger nucleophile. Okay? It's a stronger nucleophile. Okay, can. Then after that, curly arrows. Like this. Perfect answer, no problem. So basically we have a deprotonation. Then after that, electron density you push all the way to the cyano group. Okay, some of you might ask, can I don't push all the way? I forgot whether we accepted whether if you don't push all the way, but the group is there for a reason, and I think we sort of emphasize the withdrawing nature. So I think you should push all the way. Okay, so but whether we will give you the credit or this, again, that's not the discussion now lah. Yeah, so we will give you the almost perfect answer when we discuss in this kind of platform. Yeah, there isn't a need to showcase other things, so you can always save your time to get other marks later on. Okay, so just move on and that's it. Yeah, okay, so I don't think, okay, let's see my other student. You see? Sorry, I mean, I don't know. She always compound 4 lah. A lot of us also do that, right? I mean, well, not a lot. So keep it open. Let the examiner interpret whatever you want. So must be specific. Okay? Yeah, so that day when I marked her one, I was very happy. For once, everything so nice. So I put a good here. Yeah, because the interesting thing about this student is that she never attempt any stimulus base for all her exams, even in Hwa Chong. Yeah, because she said I want to do the rest. Then I want to get all the rest of marks. But in the A level she did lah. Okay, so it's not so. Yeah, and then she's a happy student now in dentistry, right? Yeah. So I hope it motivates you. So to actually, doesn't matter what you get here, as long as you work hard, your A level results will be will be more than fine. Okay, don't worry about it. Yeah. Okay, let's move on. What is this? Oh, okay. Actually, the clue is given. I forgot the question even. Yeah. Yeah, so the clue is given. So you have to push all the way. Yeah, so in this case, I need to take back my words. I think we have to push all the way to the CN, unfortunately. The clue is given to you. Okay? For part D, 19 fluorine NMR, as good as it gets. If I don't remember wrongly, most of your seniors get it correct because it's basically looking at symmetry. Okay, yeah, so I don't think it's a major issue. So compound 9, we have one signal, it's a singlet. Okay, compound 10 would be a doublet lah. 2 signals but both doublet. Oh, okay. Okay, maybe let me emphasize. This is not necessary lah. Not necessary. I just put there to keep people, your friends thinking lah. Not necessary. Okay, just tell me got two signals. Okay, yeah, I think this is not. Yeah, so back then, right? We spent a long time drawing this to make it look damn nice. I hope. Okay, yours is 2D lah. Okay, not 2D. Yours is not colored. The actual one is colored. So in the actual test, we even flash this for the student because it's colored, ma. So it's nice. Yeah. Okay, what did they? Oh wait, sorry. What was asked? Oh, why compound 9 is non-planar and 9A is planar? Okay, so they ask you why. Okay, so how do you get the motivation? Okay, so the motivation is that, okay, I mean, what is the purpose of asking student this question? I think the purpose is number one, right? In H2, we often say that the lone pairs of electrons on phenol, right, will partially delocalize into the phenol ring. That's because the O is sp2 hybridized, so-called, right? Yeah. So in that case, I think this particular diagram showcases it entirely well. Okay, because it's planar. So we say that the lone pairs here delocalize both sides. Okay. But wouldn't my sulfur also have lone pair? Yes, it has lone pair, but it's 3p. So there's orbital mismatch. And it's not asking you too much because we are showcasing you that the actual structure is indeed puckled. This is called puckled, in case you are not very sure what should you write it like. Or you can say it's like a bowl, but it's puckled lah. Okay, so yeah, compound 9A is planar, etc. lah. Yeah, so great extent of conjugation. 2B is yeah, okay, so you just be a bit careful about this, like what is they cannot effectively. Okay, so this sentence can be improved, but the main thing is, of course, the lone pairs on sulfur is in 3p, or rather sulfur is period 3 lah. Okay, so if it's going to be sp2 hybridized, then the lone pair will be in 3p, which will not overlap effectively well, or it doesn't effectively, it's not able to overlap efficiently. So in that case, cannot overlap efficiency, then I'd rather be sp3, because in that case, I am improving on my steric, meaning I'm removing myself from any potential steric interference or hindrance. Okay, yeah, so that's why it's puckled. How come this kind of question can be asked here? Because we gave you the diagram, we showcase to you what it's like on your end. You can make the necessary linking. Okay? Okay, now comes the most beautiful part. The NMR. Okay, so by using the NMR, identify the kinetic and thermodynamic products. Okay, so the NMR is here. Okay, actually, right, this question we just need a very simple response. What do we mean? Okay, so all we need you all to do, right, is based on your basic understanding of what kinetic and thermodynamic product is, let's look at temperature lah. Okay, so the temperature is the main thing we focus on here. So you see that we start off with 80 degrees Celsius, 16 hours. Then after that, we increase it to 120 degrees Celsius, 2 days. Okay, then of course, if you want, you can look at 100 degrees Celsius, 16 hours as well if you want. You notice that as the temperature, right, increases, okay, there is actually a greater proportion. There is a greater proportion of 6. Okay, actually the graph is written in such a way that you are not supposed to go and measure the height of this, so no need to measure the height. So just roughly look at the area under the graph. So you notice that there is indeed an increase from here to like that, and then this actually drops in magnitude, right? So this increases, this stays about the same, except that you notice that it becomes more defined. It becomes a lot more defined. Okay, and then after that, everything else becomes this, and then this portion disappears. Yeah, it disappears. Okay, then yeah, that's all you need to say. Like when I increase the temperature, I am getting exclusively compound 6 over a long period of time. So thermodynamic product. Then kinetic product, lower temperature, shorter time. I get both, of course, one more stable than the other. Yeah, so you can sort of mention that in your answer. Okay. Um, of course, the student wrote a lot of things, which is fine. But again, my worry lah. Uh, in fact, it's for everybody because the advice I talked to some of you in the past few days. I think the main thing is to do well in H3, right? Is content is one thing. You also need to improve a bit on your speed, but cannot anyhow rush lah. Huh? Cannot like everything just do write a few words. Yeah. So for those questions you are very excited about, you write a lot. Maybe you cut your answer by 1/3. Then you focus on the back. Then maybe you can easily ace it. Maybe get a merit in your prelim easily. Okay. And then A level is not an issue anymore. Yeah. So I think okay, but it takes time. Sometimes we're very excited about certain kind of question that wow, it's so exciting, like so easy to write. I just want to show. Yeah, but sometimes a lot of things written may not be necessary. Just something for you to think about. Okay, so yeah, quite a lot of interesting ideas here, but really we may not need all this. But so the main thing here is really the shorter period of time, which I thought we should focus on over here, this portion, and then showcase the kinetic product, and then therefore showcase the thermodynamic product. Okay, let's look at what yeah. So as usual, very short answer. So yeah, so just directly answer. This is thermodynamic, this is kinetic. Why? As temperature increase, and then NMR correspond, this thing disappear. Show that high temperature more variable. Of course, actually can write a bit more lah. Okay, like yeah, but okay yeah. Anyway, this is not marking for marks lah. Just giving the ideas will do. Okay, can so have a balance. In case you are wondering, let's say, don't worry, we'll upload the answer for you all. But I thought I just want to showcase this. In case you're wondering, what do we look out for? Yeah, very simple ideas also. Our answers always very short. Yeah. Okay, so greater proportion, the signal is proportion. Yeah. Just hit the main point. Yes? Yes. Don't worry, yeah. Yes, okay, can. So no, but as I said every exam is different okay. So although this exam our answer is so short, another exam also very short, but it is the process of learning and the thinking part, the linking part, to be able to come up with such a short answer. I think that's the beauty of the subject also lah. Sometimes you look at it, I need to write a lot, but actually after all, you summarize it into a shorter version. That's possible. Okay, yeah. Wait, where am I now? Oh, okay. F2. It was found that okay, so this is an interesting development in the question. So back then I think I was discussing with Mr. Lee, then we wanted to have a extra interesting part. So we need to give the students this particular detail in order to sieve out the answer lah. So using the above information, explain why 17, 18 are not observed, as well as the model reaction between 2 and 4 lah. So where is the model reaction between 2 and 4? The model reaction between 2 and 4 is actually here. It's actually here lor. Okay, how should I put it? Okay, first of all, right, this model reaction, right, I don't know whether you all recognize this important thing lah. The mono substitute is not the correct word, but yeah. So if you have one equivalent of your thiolate coming in, you notice that the sulfur, okay, I highlight the sulfur, right, is always 1/4 position away. You all notice that? That's what it means. Yeah. Because if this is not true, right, I will have observed other things like this. But it's not observed. They told you it's not observed. Yes. So because of that, they found out. I mean, true or not, I really don't know. Because we need to do more experiment. But they found out that this is true. They found out. They found out. Okay. How did they come up with that conclusion? Because of this. Not observed. And then you get exclusively this. Okay, so the researcher didn't observe this, and from their earlier research, blah blah, and then now they found out that 9 is the exclusive one. So they came up with the ideas that okay, this is true. Okay, they say I mean, true or not, I really don't know. I mean, currently, yeah. Okay, then after that they ask, how come eventually I'll end up with some product lah? So this model reaction actually helps, and then why I only get certain product but not the rest, right? Okay, so you need to look at the story here. Okay, so some interesting, like okay, then because this is form, etc., then etc. Okay, then okay. So sometimes teachers will read, don't know what. Okay, so we'll go back and think about it lah. Sometimes we'll come and revisit the scripts. Okay, because we also don't want to penalize the students unnecessarily lah. But of course there are some correct ideas which is here, which is good. Okay, so let's see what the seniors wrote. Okay, so I think it's written in a very slick way. Since there's a higher proportion of 4 in the reaction mixture, 2 will undergo more than once, and then okay, so this is purely words. Purely words. Okay. But how can we come to terms with it by simply looking at this? Looking at a diagram. Like this is not observed. Okay, so what we can look at is the reason why we get this 16, right? You can picture it like that. Because this thing is crisscross, like this. Remember what we said just now? 1/4 position, stabilize the charge. Remember, every time I attack, right, I will push, then there must be a minus charge stabilized somewhere. Yeah, so that's what they mean. Then that also means that this is not possible lah. This is not possible because I do not have the opportunity for that crisscross 1/4 relationship. Okay, then you will ask, then how to get this? Very simple. This thing can open up, and then the other one can come in. Yeah, so that is the dynamic self-correcting part. That's why in the end I hit, I will get 6. So that's the whole story behind this lah. Yeah. Okay. So the little simple answer we have is like that, but actually have some faith in your own answer, please. Okay, but this is what I will write if I'm the student. Actually, Mr. Lee and I, or rather, Mr. Lee came out with the answer lah. Then the teachers we gave a bit of input as well lah. So there's an excess of 4, so 17 is formed. Then activate the ring. I think this is the main part lah. To give this and this. So the later is not observed. Then you have to quote this thing. That's it. Yeah. Okay. Yeah. Yeah, so not to worry. Sometimes the students, you are not very confident of the answer, but actually what you wrote is correct. It's just that maybe it's a long-winded way, but it's fine. Okay. Suggest X and Y to get 1.3, right? Okay, I think this is fine because what did you actually notice about this thing? Wait. Okay, you notice that it's a pattern recognition kind of question. Like this portion, right, okay, is actually found over here. Okay, or rather here. Yeah, so it branch out. Okay. Then yeah, so as I said, pattern recognition. Then in that case, how should this whole thing look like? So if I'm going to color code, it seems to be like that. Yeah. Oh, yeah, I think you need highlighter in exam sometimes. Okay, so it helps you. Yeah. So yeah. So that's of course this is, I mean, this is part of it, but from another perspective, what you can see is, okay, show you you can see is this thing like that. Okay, and then after that this thing, wait, let me see, this thing like that, okay, and then this thing like this, and then this thing like this. Okay, so they come together, they whack. So which part do they whack? They whack the middle, this portion, this portion. Yeah. So remember just now, the portion that the sulfur whack is actually the floral-based aromatics. So with that idea in, ta-da, yeah, that's the answer that you can come up with, because, and that is the idea. I think later on they ask, why is it called a 4-point junction? Okay, because you realize that this thing can go, oops, 3 direction. I mean 3 point, like that. Okay, but this thing goes 4 ways. Yeah, so it expands up, or okay, maybe this part might be a better example. This portion. Yeah, so it goes 4 ways. So it's called 4 point. Okay, so here, 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 and here. Okay, yeah, so that's why it's called a 4-point junction. Yep. Yeah, so it's pattern recognition. I mean, this is like polymer, but not exactly polymer chemistry. Okay, then although 19 has a greater cavity, okay, so I think back then, when we tested this, we sort of realized that actually this question is a bit difficult to answer. Yeah, so basically any ideas that the students write, I think we'll just mark you with the correct credit lah. Like some ideas, for example, in this case, structure is rigid, twisting at sulfur bridge restricted. Or there's some ideas to tell us why it is smaller or bit smaller. Okay, then of course, what is the most important application? Got hole, right? Can filter things lah. So molecular sieve is one thing. So there are a lot of answers we accepted lah, related. I think we have a few like storage of gases. Okay, these are very important application. Yep, that's it. Okay, come. The question very long, I realize. Sometimes I also look back at myself. Like, how come the last time how come we can set such disgusting long question? Sometimes we look back, when we anyway, Mr. Lee asked me to remind you all to do the 2019 paper, which is supposed to be debrief or review when? Next Tuesday, right? Yeah. Yeah. So that day I saw it, I said, wow, stunned. Oh, back then quite difficult. Yeah, I don't know lah. I think can. Or is it once we teach for a longer time, then maybe the question we set become easier. I don't know lah. I also don't think so. But anyway, I think this was set over a period of few years because we gave this to your great grand seniors, a few batches, different combination of this idea. Actually, I really love this the Hammett equation. I was really hoping that it will be in the H3 syllabus formally, because it's really for a very simple reason. Because it is the fundamental of understanding electronic behavior. Like if something is electron donating or something is electron withdrawing, how do we know that? We know that from the Hammett equation. Yeah. So because of that, then this question was developed over a few years. Different seniors get different versions. Okay, but from here we combine some of it. Okay, so I just share this question with you. I don't think I can, if I can't finish this, then you know, the remaining part will upload we will upload everything, all the answers are back. But if I can explain everything, I'll explain everything. Okay, so I think first of all, contextually is very heavy because you need to understand the question, like the equation. So what exactly is sigma? Okay, so sigma is actually a constant. That is the law of the ratio between the K with the substituents, which could be meta substituted or para substituted. Okay, then H is of course the original, the benchmark, which is benzoic acid. That's why benzoic acid is so important for over 200 years because it has always been used as a benchmark. And people are able to study electronic effect and electronic effect solely because the benzene ring you allow or you are able to bond different groups, and then the withdrawal and donating effect is very obvious because of the pi electron clock. Yeah, so with all these factors coming in, these are very old science. If you're interested, you should read about it. In university you learn it in the first year, very briefly. Okay, and they will ask it in exam almost throughout your university days. Related, if you are looking at questions related to mechanism. Okay, so from here, they tell you about the different sigma. Okay, but you need to keep referring back. What exactly does sigma means? If you don't refer back, sometimes you will be a bit lost. So basically, withdrawing groups have a positive sigma, donating groups have a negative sigma. The one which stood out is actually where is it? OH. And then of course NH2 as well. But NH2 not so obvious. That's why we didn't ask. Okay. Then after that, first they ask you explain why electron withdrawing group large positive sigma, donating group negative. Okay, so we can look at a simple response like this. Definitely not an issue. Perfect. In fact, so you have the okay. I saw something weird, but never mind. Okay, this is supposed to be sigma. No wonder I keep thinking. Okay, just be careful in exam. Okay, so sigma. So withdrawing group. Okay, what is the proper explanation, like super perfect kind of explanation that actually I would really hope people can write. But okay, you see, right? Your withdrawing group, right, actually do not really allow the negative charge in the carboxylate to delocalize into the benzene ring, right? Do y'all recognize that? I don't know whether what I said makes sense to y'all. So for example, if I have the phenol ring here, you'll notice that this region of the negative charge actually it just stays within the carboxylate. Although there is overlap, but you cannot draw a resonance structure because once you draw something, the CO2 gone. Cannot. Right? So so actually what would a perfect answer be, or maybe I shouldn't use the word perfect, or what would be a more accurate answer be? Actually, right, what we are really looking at is the extent of delocalization. So if I have a donating group, I am enriching the phenol ring with electron density. So there is slightly less incentive for the carboxylate, right, to overlap. Yeah, so it's about overlapping or partially overlap of electron core. But if I have a withdrawing group, I am depleting the phenol ring of electron density. So there is a greater incentive for the carboxylate anion to share a little bit more of its electron density so that it's slightly more stabilized. Yeah, so that is the main idea which if you can, you should mention that. But in most cases, students, even our grand senior, all this, they do give similar ideas. So you might want to, although sometimes we can close one eye, but you might want to avoid writing things, for example, donate electron density to the carboxyl. Because the electron donating behavior do not exactly interact with the carboxylate, but it donate electron density to the phenol ring, and then whether the carboxylate can delocalize more or less depends, or overlap more or less. Okay, so just be a bit careful. We're not so stringent on nitty-gritties. That's why, in exam we don't really deduct marks based on that. Okay, and then of course, maybe just share with you some of the expressions. Sometimes I feel it may not be necessary. That's why sometimes when I mark, I always write things like expression could be refined. Okay, that's the reason. So for example, this particular senior, I think she wrote electron withdrawing group withdraw electron density from the benzene ring, dispersing the negative charge of the conjugate base form. So okay, so after that, maybe remember that, oh, actually I need to talk about benzoate lah. So I put a benzoate there, making it more stable. Okay. With a more stable conjugate base, the benzoic acid will dissociate to a greater extent. Okay, so then increasing KS, so the electron donating group intensify the negative charge of the benzoate. So this portion is a bit problematic lah. Intensify the negative charge. Okay lah. I mean, destabilize it. Yeah. So So I think the main thing, as I said just now, is about are you withdrawing electron density away from the phenol ring or enhancing the electron density of the phenol ring, and in place whether the carboxylate and ionic electron core can overlap more or less. So that will be the perfect explanation if you want. Yeah, but again, we can always settle for somewhere that is not so perfect. But again, when you want to learn concepts, make sure that you get the correct ideas in. Okay. This is the interesting part, which is asked over here. Okay. Why metal OH has a positive sigma but para? Okay. So you may find appropriate to draw resonance structures. Okay. So again, okay. Actually, on hindsight, your friend actually drew the one with the carboxylate anion. Actually, on hindsight, I think it's fine. I mean, there's nothing entirely wrong lah. Okay. But if I'm the one, I'll rather draw for this, so that is to impress upon the fact that the incentive of losing the H is much lesser. Just because of the donating effect. So it kind of like already before the system can lose the H, the region around it is already relatively electron rich. Yeah. So it's about looking at the transition state also in losing the H. So when the H is about to be gone, you need strong, maybe stronger bases, but H2O itself is not that strong a base. So the tendency to lose the H is not there. Okay, but do we really need to like drill down on the nitty-gritty? Actually, no lah. So I mean, to be honest, if the students can produce things like this and to tell us that in this case your OH is pi donating, but when it's meta is sigma withdrawing, I think that's perfect already. It's fine already. Yeah, which is indeed what was mentioned here lah. Yeah, and then after that, for the meta OH is only a sigma withdrawing effect. So you can just emphasize the sigma electron withdrawing effect. Yeah. Okay, via the sigma bonding framework. I think this is the term I often use. Okay. Then let's move on to the next bit. Okay, so the reason why I really love Hamed equation and the plot is because it showcases to you mechanism. Because a lot of you ask, those are very good questions. A lot of you ask, how you know that addition elimination must be like that? You know, you often ask like, for example, this is the classic law. How do you know that? Like, why I draw like that cannot? Why like that cannot? Correct what? Nothing wrong. You know, like, when you learn H2, you often ask, right? How come the hydrolysis of acyl chloride, I cannot just wet and kick out the Cl? Remember, those are questions you ask, right? How you know must break the pi bond first and then kick out? Sometimes there isn't a perfect answer if you don't know the Hamed. And you realize that Hamed, they are very, in the past, they were just very, very hardworking, looking at various systems, studying thousands, tens of thousands of reactions, and then come up with all these plots. So it's amazing. So that's what they did. Yeah, so all the questions of how you know it's true, how you know that's true, it's proven by Hamed. Not proven, supported by their hypothesis. Okay, so over here, right, you have three postulates. One is attack kick out. Okay. One, you develop a negative charge at the O. The other one, you develop a positive charge at the O. So how do you know? Well, you look at this. This explained to you. Yeah. So if the rho, this rho is greater than 1, sensitive to substituent, so negative charge is building up in the rate determining step. Then in between, negative charge is building up, but it's less sensitive to the substituent effect. And then close to 0 means no charge is developing, less than 0, positive charge is building up. Okay, so clear cut. Then after that, they ask you, the rho value for hydrolysis of ester is this. Suggest a suitable rho value for the other two. Okay, so again, from here, positive rho value means negative charge is building up. Okay, so data interpretation. So you realize that actually you realize that if you learn Hamed postulate, Hamed equation, there are a lot of questions we can ask you. Thousands of kind of questions. We just give you a lot of graphs and then you interpret from there. Yeah, but in the end, it's not in the syllabus. So yeah, that's why I cannot ask. Yeah. So if there's no charge if there's no charge building up, then postulate 1 is correct. Not correct, but if rho is close to 0. Then postulate 3 will be positive charge building up. So rho is negative 1.5. Okay, just a simple appreciation like this will do. Okay, so let's see. Yeah, so I think back then also your senior wrote this. Okay. Oh, okay. Now I saw this, right? I remember why I want to explain it. Okay. Sorry to go back to not go back, but I'm sure you can remember just a little earlier part on this. Because during marking of papers, right, I often remember one thing. Whenever the question asks the student to draw appropriate resonance structures, right, the student will spam. Okay, we're all learning, so let's not laugh at our senior or what, your seniors or what. But let's ask ourselves one question. When you draw the resonance structures, right, what are you trying to showcase? If you can answer that, then draw. If you cannot answer that, don't draw. Yeah, as simple as that. So don't draw and draw, and then you don't know what is the outcome you want to showcase to the examiner. That's very important. Yeah, so I think my suggestion is, if you know what you want to showcase, then you draw. If not, then don't draw and draw without explaining. Okay, so sometimes it's only just 2 structures. That's it. Enough already. Okay, yeah. Anyway, I come back. Okay, anyway, I think I'm done with this. So I'll move on to part C. Okay, so for part C, you have some of the rho values for the ionization of benzoic acid. Okay, actually this is very beautiful chemistry because you realize that different solvent, you get different rho value. So they really realize that the sensitivity of the substituent is related to the solvent as well. Yeah, so from here they ask you, by considering the interaction So you know it's ion dipole interaction or hydrogen bonding with water lah. Why the rho value of benzoic acid in 95 is significantly larger lah. So larger means more sensitive to substituent effect. Very important, you need to recognize it. What's the meaning of more sensitive to substituent effect? Means if I change it to a donating or withdrawing group, it will swing the gradient, the rho gradient. It will swing this gradient if I plot this against this lah. Yeah. Okay. Okay. So let's. Oops. Okay. So the answer. You have ion dipole interaction. Okay. So water molecules are smaller, etc. Then after that, bulkier. Yeah. So I bracket this part. So that's why I know what to talk about. This is the main point. The dissociative is more sensitive to the change in electron density of the carboxylate moiety, and because of that, it is more susceptible or more sensitive to substituent effect. Yeah, that's the main point I'm looking at actually. Okay, yeah. So anyway, for your information, if you didn't catch what I said, the session is recorded, so you can view it later if you want. Okay. Yeah, because as I said, for the benefit of some of the students who cannot be here due to the injection. Okay. What else I want to talk about? Okay, I think that should be enough. Okay. Okay, then you have another disgusting portion, which is part D. Which is almost a perfect question in that sense, because it's just that certain parts were taken out. Okay, so first, I want to highlight one thing. This is the RDS, this is the RDS. You must watch properly. Where's the rate determining step? Okay, so first, pathway A, deprotonate the protonic hydrogen from the carbamate. This is called carbamate, by the way. You don't have to know the name, but this is called carbamate. It's not amide, because the other side got O. Yeah, but no need to know, as in just to tell you, okay? Yeah. And then after that, the electron density get pushed, or rather, the small molecule get expelled. Now, people, important thing to take note of. In this process, right, because this is the rate determining step, right? What do you notice? The negative charge is developing at the phenoxide oxygen. That means that any change in X will make it sensitive to substituent effect, right? Because the negative charge is developing at the O minus, O minus, you know, negative charge delocalized in the phenol ring. That's the main thing you need to recognize. But pathway B, your rate determining step, right? Whack the carbonyl carbon, develop the negative charge at the O. Substituent effect so far away, right? Important or not? Important, but not so important. As in, of course, there will be some importance. Okay? So I tell you the answer already. In fact, actually I told you the answer indirectly. Okay. Then, in the recent development leading to the development of this catalytic antibodies, wow, the effect of the catalytic antibodies on the hydrolysis of carbamate was studied using the Hammett plot. Well, this one is quite daunting, but anyway, you have two plots. One with the rho 0.526 sensitivity, not so sensitive. Okay, this is very sensitive. Okay, then they ask you, based on the above plot provided in parts A information, suggest whether pathway A is the one that is catalyzed by the antibody or B lah. Okay, so is it A or B here? So okay, so in this part it was written. Okay, so So in this case, right, okay, first we need to go back to the question. This is the catalyzed one. Then the rho is low, right? If you choose A, right, very sensitive, so cannot choose A. So you must choose B. Something like that, lah. As in, I just make it short and sweet for you. Okay, the first step shouldn't be taken into consideration because remember in kinetics, yeah, when you measure rate of reaction, is the rate determining step is the one you need to focus on. Okay, so that will be a simplified version of the answer I can give you. I don't want to go on and on and on and on because I think at this late hours, any more words from me will probably not make you awake. Okay, but I will say that go and think about it. Okay, now with a refreshed perspective of what I shared with you, you can think about it. And then later on at home, you can go and look at the uploaded answers, which we give to you all. Later on, then you try to read and see whether it makes sense to you. If not, you can re-watch the video of the presentation today. Then you can think about it, lah. Okay, so I mean that's I thought that's what I can share with you the main ideas which is important in our discussion, lah. Okay, then the last part, just the last bit I thought I can go through is actually this part on part E, lah. Okay, so on part E, right, again we have this particular reactions. It's a nucleophilic addition. I think most of you should be able to tell. Okay, you should be able to also tell that this is also related to what you learned in your 2,4-dinitrophenolhydrazine, in case you are not so aware. Yeah, okay. Resonance structures, I would expect all of you to be able to draw reasonable ones, lah. So to be able to showcase that the other two lone pair delocalize into the carbonyl oxygen. Okay, and then the other lone pair get delocalized as well. Okay, can. So I think this is something that we will expect you all to be able to draw. Okay, in fact, yeah, for this particular simi, yeah, I think it was also drawn in a very clear manner. In fact, right, I would actually prefer this version because in the sense it showcased that oxygen is a better electrons sink because it takes on the negative charge. But again, who are we to say which version? Because in actual fact, it's all in between. Yeah, so there shouldn't be a judgment being put on which is a better version. Yeah, but it's a personal preference, as I said. Okay. Then based on kinetics, this particular plot, straight line, okay, K observed, straight line, remember, K observed, sigma. Okay, apparent order of the reaction. So I think a lot of you might have seen the per minute. Yeah, so it's first order. There's only one concentration. Yeah, so I think simple ideas like this is fine. So again, it's like a repeat of the ideas in front. You notice that donating group tends to be here, withdrawing groups tends to be high up. Okay, so which showcase the rate of the reaction. Okay, quite prominently. Then over here, based on the above graph, comment on how the nature of the substituent effect affects the rate of the reaction. Okay, then your first step involves the nucleophilic attack. Okay, so electron deficiency play a very important role. Yeah, so your substituent effect again is important because your withdrawing groups will make the carbonyl carbon more electron deficient. Because if you look back at the structure, it's like that. So electron withdrawing groups will make the carbonyl carbon more electron deficient, more susceptible to nucleophilic attack. Donating group will make it not as electron deficient, so not so susceptible to nucleophilic attack. It's always in comparative terms. Okay, then that's about it. The last bit is the mechanism. Okay, it's a bit sneaky, but I can show you one little thing, which a lot of you, I think you didn't read that part. It's buffered at pH 1.75. Yeah. So acid. So protonate first. Yeah. So everybody made the similar mistake.
Okay, the second last part will be looking at part F. Okay, maybe before I continue, right, I would like to stress that part F is actually not in your H3 curriculum. Okay, it is very explicitly mentioned in the syllabus document that for your current H3 syllabus, only um, nucleophilic substitution, okay, and some form of addition elimination is in your syllabus. Yeah. So electrophilic addition, which is the theme for part F, will not be in. So don't worry so much about it. Just take it as a form of practice. Okay. It's actually in your grades grand seniors the old syllabus for pharmaceutical chem. Okay. So for this particular parts, you are told that stubin exists as two stereoisomers. Yeah, so given this particular formula, you should be able to tell that it consists of the E and the Z isomers. Okay, because you have a phenyl ring bonded to a carbon and then bonded to a H, double bond to a carbon, and then of course you have another phenyl ring and a H. So it can either exist as the E or the Z configuration. Okay, so you were told that when it's subjected to bromine dissolved in CCl4, one stereoisomer of stubin gives two stereoisomeric product J and K. Okay, and the other one gives only one. So if you kind of recall, or if you try to draw the mechanism out, which you're supposed to do so, you will realize that L is actually a meso compound. Okay, so you are asked to rationalize via suitable reaction mechanisms how J, K, and L are produced, and then you need to use appropriate curly arrows to show the electron pair movement and then indicate clearly the relationship between K and L and then J and K. Okay, so without further ado, we'll just take a look at your classmates' scripts. Okay, so you can either start off as a flat configuration like this, okay, or if I may suggest, you could actually draw it out like this, okay, showing the projection out, okay, and then showing the projection in, and then of course the pH the H projecting out, and then another H projecting in, okay, something like this. Yeah, so that you will kind of like realize that after the reaction took place, this is the carbocationic intermediate that you will get. Okay, so electrophilic addition, bromine delta plus, bromine here, delta minus. So you push the electrons towards the bromides, and then you will get this particular intermediate. Okay, and then after drawing it, you realize that these two compounds are actually the same. How do I tell? So basically, what you can do is you will rotate this whole compound, rotates 180 degrees. Okay, so if I rotate 180 degrees, I'll get pH to be here, and then the other pH to be here, and then the rotation is not into the paper or out of the paper, just around the paper. So the BR will be projecting away from you, and then another BR will be projecting out towards you. Okay, so you realize that they are actually the same thing. Okay, so it's not an issue, so we call this the meso compound. Okay, if you start off with the Z isomer, you will end up with an enantiomeric pair. How do you actually tell that they are an enantiomeric pair? Well, I think first of all, you realize that the chiral center actually flips. Okay, another way you can do is you will rotate 180 degrees into the plane of the paper. Okay, so when you do that, you realize that the pH is like this, and then the BR is projecting towards you, and then the other PR is projecting away from you, and then oops, sorry, this like this, like this, and then the pH is like this. Okay, yep. So if I try to shift this over here, then you realize that they are actually an enantiomeric pair if this is the mirror plane. Okay, yep. So relatively straightforward, and this is definitely in your curriculum. You need to be able to tell the difference between enantiomeric pair and diastereomeric pair. So if you are able to do that, then I don't think part F is any big issue. Okay, yep. And then for the final parts, you were told that in the addition of bromine to mono-substituted stibine, Ross and co-worker have argued for the competitive formation of the three discrete intermediate as shown. Okay, so basically what they are trying to share with us is that it need not be a cyclic bromonium intermediate. Okay, it could be one with the plus charge at what they define as the alpha carbon. Okay, or it could be the other one with the plus charge at what they define as the beta carbon. Okay, or it could jolly well be the cyclic bromonium. Okay, so what they did was, in order to study the rate constant for the bromination of the 5 mono-substituted stibines, right? They actually tabulated the results and then plotted a Hammett correlation graph. Okay, so what you realize is that if I have a NH2, okay, which means very strongly electron donating group, you realize that the relative rates is actually quite fast. So you're going to get a K observed of about in the magnitude between 10 to the power of 5 to 10 to the power of 8. Okay. However, if you are getting relatively or pretty strong electron withdrawing groups, and you are going to get a K observed in the magnitude of unity. Okay, and then of course the rest will be somewhere in between like 10ish to 100 plus. Okay, then so for G part 1, you will ask if X is a strongly electron donating group, it is found that the K alpha is much greater than the rate constant for the cyclic bromonium and that for the one at the beta position. So they ask you to use a suitable substituent from the table and explain why this is so. So if I want a strongly electron donating group, to be honest, I only have one choice. Either OH or NH2, and most of the time I will choose the extreme lah. Okay, and of course between NH2 and OH, NH2 is definitely a stronger electron donating group. It should be pretty obvious to you. The reason being, nitrogen is less electronegative than oxygen, so it holds onto its lone pairs of electron less strongly. So that means that the lone pairs of electron is kind of like more willing or more willing to be part of the delocalized electron cloud where possible. Okay, so I will choose NH2 and your classmate chose NH2 as well. Okay, so with that coming into the picture, a resonance structure was being drawn showing the delocalized structures. So you realize that there is a stable form because the lone pairs of electrons, I can push the electron density all the way to the positive charge. Okay, and this actually helps to stabilize the carbocationic intermediate. Yeah, but for the other two, you realize that electron pushing is not possible. I mean, it's not that it's not possible, but in this case, it will not be very much influenced by the electron donating nature because the carbocation will not be appreciably stabilized. Yeah, so if this particular carbocation can be appreciably stabilized, then it will be formed in much greater quantity as compared to the rest. Okay, and then for the case of the cyclic bromonium, well, I mean, there's no stabilizing factor to talk about. So in this case, its formation, again, I wouldn't expect a lot of it to be formed. Okay, and this is kind of reflected again by other experiments, which is not shown here, and of course, in this particular case, is by the information given to you. Okay, and then the final part is the interesting one because they said that Ross and co-workers postulated that the type of intermediate form in the bromination is largely determined by the nature of the substituent. So they concluded that strong electron donating group favors the formation of alpha carbocationic intermediates. Okay, the withdrawing group favors formation of beta, and then you will ask from the graph whether you agree with their postulate or you do not agree. Okay, so I think that's fine. So you realize that from this particular graph, right, you can actually split them up into roughly three portions, and it's not really a straight line. You can see that the decrease, it goes from, it's like this, okay, for strong electron donating groups. Okay, so let me draw the gradient in a nicer way. So it's like this. Okay, so it's like this. Okay, and then after that, not so strong donating or weak withdrawing groups, it's like this. Okay, then for withdrawing groups will be like this. Okay, so normally graph like this with a changing gradient, right, as I as my as the nature of the substituent change, right, it represent a changing reaction mechanism. Okay, so from here you realize that the reaction mechanism is likely to change from something like this to maybe a cyclic bromonium, maybe, and then to one where, because I have a withdrawing group, I want to prevent the carbocation from being next to the withdrawing group, so no go for this. And in the case of my cyclic bromonium, you realize that the concentration of the positive charge is still around these two carbon, but it's somewhere smack in the middle. So in that case, I want to be as far apart as possible. So in this case, this intermediate is preferred. So to some extent, from the graph, you can see that it does support a changing mechanism, okay, when my substituent changes from strong electron donating group to strong electron withdrawing groups. Okay, so in that sense, I would tend to agree, and let's see what your classmate wrote. Okay, so agree partially. Okay, so it's a not too bad, it's a partial agreement. Okay, so electron donating is present, okay, sensitive, so it's evident by the steeper gradient. Okay, so this is the key idea. So therefore the alpha intermediate is favored since stability is significantly affected. But if I have a withdrawing group does not vary very much, okay, so does not vary very much, does it mean that it is changed to a cyclic bromonium, or does it mean that I have an alpha carbocation intermediate? So maybe I need to perform more experiment to be a little bit more conclusive. Yep, so that could be an idea that which you can give. Okay, and of course in our so-called the model answer we give to the students would be pretty much similar to what your classmate wrote. So notes that there's a changing gradient. Okay, when X is changed from strong donating group to weakly donating to strong withdrawing groups. Okay, so it indicates that a strong donating group, so this is likely to be the case. Okay, so as per all assessment or as per all data, I would like to emphasize that it will be good if you can use to the best of ability as much of the data as you could, so that it showcased to the examiner you actually read through the information. Okay, so for a weak donating group, maybe this is maybe okay. So for me, I will feel that this could be the case. Yeah, because the positive charge developed is slightly further away. But for a strong withdrawing groups, then it is likely that K beta, which means the formation of the beta carbocation intermediate is likely to be favored. Okay, because in that case, the withdrawing nature of the electron withdrawing group, right, will not be able to affect the stability of the carbocation, or rather will not be able to affect the stability or cause it to be destabilized as much as if it were to be a cyclic bromonium, or if the carbocation were to be in the alpha position. Okay, yep. So yeah, back then we actually asked the students this question, and yeah, we got pretty decent answer. Okay, so I think that's about it for the review of problem set 2. So I hope you found the question challenging, and I think in the next session we'll be doing the prelim paper 2019.